Hello. This lecture is the first of a new set of modules on supply chain optimization. We're going to be looking at global supply chain optimization because clearly we're in a global economy. People don't just do this only in their backyard. We have to look at multimodal or intermodal, meaning multiple modes of transportation, because in most of today's supply chains, things are not just done by a single mode of transportation. So when I think about overviewing this topic, first I want to think about, okay, who are the players or who are the interested parties in this intermodal supply chain that we're worried about? Well, this idea of intermodal international logistics is, like I mentioned, truly in the global economy. We have a lot of key players. These are operators of ports, because if we're dealing with shipping stuff on the water, clearly the ports are the key location where the goods arrive from various places in country to get on the large container ships. Airports, because we do have, often at a quicker speed but at a higher cost than boats or trains or rail, we could use air in emergency cases, or maybe we have certain things that we do fly in, such that the operators of airports are players in this discussion. The container terminals is where the different types of goods coming from various suppliers will come in and get packaged into the containers that then get stacked on either boats or trains or both. In some cases, we have, like at the Port of Charleston, where a container ship will come in, then the container boxes get taken off the ship and put directly onto the back of an 18-wheeler truck whose trailer is specifically made to hold these containers to be on the road, like a J.B. Hunt or a Swift. Freight forwarders, people who kind of make it all go. I know we have some potentially in the cohort here, but freight forwarders are obviously key players in this because we have a lot of expertise in kind of being the liaison or the glue or the go-between or the engine, if you will, that makes this process work. Cargo handling services are another key portion, and I want you to realize that when I say the container is the key unit of transfer in the typical global supply chain, clearly lots of stuff can be containerized. But there are other things, coke drums, different parts of the EPC industry. I've heard the term high, wide, and heavy. These type of hauling obviously isn't going to be in a container stacked with a bunch of other containers on a boat. There are other problems we deal with in the capital projects industry of hauling unique types of things over unique types of terrain in unique locations. So these may not fall within the standardized container, but for the purpose of kind of overviewing the network and the lecture in terms of a global supply chain, let's just keep in mind that predominantly, while we may be handling containers, there are often a variety of different containers that might be used, or in some cases of the high, wide, and heavy, potentially we don't have containers at all. We're just actually hauling the individual item. So I found one of the papers I posted for you was a very early paper that gave us a definition of international multimodal transport. So it talks about the carriage of goods by two different modes, at least, across different country borders. Well, when I read this definition, it seems that there are three prerequisites, according to this author, for international multimodal transport. So one is that you have to use at least two different modes of transport. Well, that makes sense, because the intermodal part or the multimodal part, those terms can be used interchangeably. We have to have some kind of transfer or switching between modes of transportation. It's not just putting it in a truck, the truck drives it to the distribution center, and we're finished. We have a transportation contract, a through bill of lading, if you will, that communicates what we're hauling between the interesting parties. And we're going between at least two different countries because we're talking about international here. We have, obviously, companies who do business in the United States that transport things across different states intermodally. But we're talking about international or the global supply chain, we're dealing with more than one country. So let's talk about practice here, because we are dealing with a case studies course. I want this module to hopefully ring true to either what you've seen, what you might have heard. I know it's what I've experienced in my industrial days, as well as my industry-focused research. But when I talk about supply chain optimization, whether it's multimodal international logistics or just optimizing a supply chain in the continental United States, I hate to break it to you, but this is typically not done with Solver. And I say that with a little tongue-in-cheek because Solver is a very useful tool for you to understand some of the basic functionality of what's capable, the optimization framework. But here, some of the packages that myself, my customers, my clients, my research partners use There's packages like Garobi and Cplex and ExpressMP. There's many different commercial optimization packages available. And I'll motivate that later in this module about why Solver really isn't the best way to handle these true large-scale problems. We might do strategic level studies where we're looking at time frames in terms of quarters or years or a 5-year plan. And often at the strategic level, when I'm talking about optimizing a supply chain's performance, I will use optimization. I might use some simulation, could be Monte Carlo simulation, depends on how high fidelity my input data is, how much information I really know about what I'm trying to optimize. But these strategic studies typically have a longer term focus. What I'll call the middle level is the tactical level of studies. Maybe here I'm looking at months or quarters, or maybe only 2 years. Here optimization is still obviously a player, but then we start looking at rules or heuristics, if you will, our own custom approaches or ways that we do business start to come into play in how we analyze these type of supply chains. And finally, at what I'll call the lowest level, or the finest level of detail, this operational level studies, we do have this idea of looking at days, weeks, maybe months at the outset, and here we're often having very good fidelity with data. We know how demand evolves over time. We have a much smaller area of focus, and again, heuristics and discrete event simulation are often used in this case. Now, I'm not saying you cannot use optimization at all the levels. I mean, I love optimization and all, but you have to use the appropriate IE tool based on the problem that you're studying. And hopefully, as we motivate the second paper in this module that I posted for you, the integration of optimization and simulation for supply chain planning, you'll start to get a feel for which tool is most appropriate for which type of problem. Because part of your capstone exercise, whatever problem you're going to end up analyzing, you and your teammates, applying the right industrial engineering skill set to it is paramount. You know, we tell students, if your only tool is a hammer, everything looks like a nail. If all you know how to do is optimize, or if all you know how to do is simulate, you're going to do that no matter what the problem is. And we really don't want to get ourselves into that mindset. So that paper talks about a 2-step process, and actually it gives more than 2 steps, but the first 2 are kind of the most important to me. I've actually done this in my industry career. It does work. There are methods to the madness here, but often we do a strategic high-level optimization study first. Now, these optimization models typically have deterministic or fixed inputs. Again, they're strategic, they're long-term. We don't know about random probability distributions at this point, nor do we care, because if I'm trying to plan out a 5-year plan over 1-year time buckets, you know, the fact that I have probability distributions on how demand is going to arrive each week is really kind of getting lost in the weeds. So this is a longer time horizon, more of a strategic study, and the type of inputs that might be useful or required in such a strategic network optimization study could include things like, if I'm figuring out site locations, a list of candidate sites and where they are located. Maybe my optimization model is going to decide for me, based on some objective, some performance measure of interest, how to locate where I should select to put my different facilities. I also could have a list of potential demand sites or customers and where they're located. Maybe the model is going to choose which customers I serve. Maybe I already know which customers I'm going to serve, and I need to figure out from where I'm going to serve them. I need to know the demands by location, because even though if I know the demand locations and I know who the demanders are, I need to know how much they need, because that's what's sort of driving the decisions we're making inside of this network. I need to understand the cost in terms of flowing goods out of a supply location or into a demand location across different transportation modes. These are all important inputs as we start to look at an optimization model where maybe we're going to minimize total cost of doing business or maximize profit. There's a variety of different performance measures that typically get used here. Transportation costs, again, could have outbound costs, could have inbound costs, costs that are dependent on mode of operation, costs that are incurred when I switch from one mode of transportation to another. You know, there's a lot of level of detail that could be added here to really give you a high fidelity model. Then typically there's a bunch of other constraints that I'll call the reality constraints. There might be some business rules that the person's company has, such as every demand point must be located within 500 miles of a warehouse. Or we must have at least one backup warehouse. Everybody has to have a secondary supplier available to them in the case where their primary supplier has a failure or is at risk of failing. There's so much reality built in where we have to use so many trucks of a certain type, or we don't make deliveries on Sunday, or and so on and so forth, such that there are often many other constraints that go into these models that once you get the basic of the flow of goods and the costing and the modes of transport, the real art here is figuring out which of the practical constraints really matter and should be modeled into our large-scale strategic model. Because as I've said before, to me a good model is the simplest model you can build that answers the question of interest to you. So, depending on these other constraints, things could start to become really unwieldy. Could be a lot of extra lifting, a lot of extra heavy work to try to model these to squeeze out an extra 0.5% when the 90% solution could be just fine potentially. So when I think about potential performance measures that people look at, that they're curious about, because remember in an optimization model, we're often maximizing or minimizing some performance measure of interest. Now, it's a whole other lecture, but typically there's more than one of these performance measures. Typically, you're not just trying to minimize cost. There's some other objectives as well. Now, the problem is those are mathematically challenging to get after, so often people pick their most important or the primary objective of interest. Such as, we're going to minimize total cost. We're going to look at minimizing or maximizing or just measuring the flow in and out of each node in the supply chain. From the suppliers, how much is each supplier giving me? How are we supplying the demand to our different customers? These could be something we try to drive towards a maximum or a minimum, or it could just be performance measures that we compute as a resultant of minimizing total cost. Now that total cost is minimized, I can tell you what is the cost optimal solution in terms of the flow in and out of each node. I also, if I have a cost optimal solution or any solution to an optimization model, we have the ability to get a breakdown of how are the different modes of transportation actually being deployed? How are they being used? Between one origin and one destination, it might say I'm shipping 50% of the time by truck, 50% of the time by rail. It could show transfers by rail, could transfer over to a truck. It could show we're going to use the maritime, we're going to use the water to use this transportation link. There are a variety of transportation modes available, and by you including them or not including them in your model as potential options or choices for the model to make. Because remember, in an optimization model, we're using a prescriptive model, which means it's going to decide the best way to do business such that our objective is optimal. If it's minimized cost, it's going to give you the lowest cost solution. If that lowest cost solution is do everything on the road, don't do anything by air, don't do anything by rail, don't do anything in the water, that is a potential solution. Similarly, depending on how much capacity you have, depending on the different modes of transportation available, the cost assumptions, the model may recommend an intermodal or multimodal solution. Could be that there are certain pairs of locations that can only be reached by a certain mode of transportation. Depending on how you model things, the optimization study will bear out the best way to operate within the constraints that you give it. I could actually look at manufacturing capacities that are resulting from the supply chain design that we come up with. Who supplies who? How do the goods flow within the supply chain is a typical output of the model. We're not going to tell it that on the front end because this is a prescriptive model. We are going to let the model prescribe for us like a doctor does, tell us what's the best way to do things. Which warehouses supply which customers? Which factories should supply which warehouses? We have a variety of different echelons in the supply chain that you've heard about in other classes. These optimization studies will give us important decisions that help us make better tactical, strategic, and operational decisions as we work to optimize our supply chain. And so on. There are many different output performance measures you can get out of these models. Now remember, these strategic supply chain studies are longer term, and they're all deterministic inputs. Every time you run them, you're going to get the same exact answer. If you change a constraint or add a constraint, the answer could start to slightly change, depending on whether or not the new constraint is what we'll call binding or active. So in other words, if you built this model and you solved it without the constraint that every warehouse has to be within 500 miles of a supply point, if the optimal solution already has them within 500 miles of a supply point, adding that constraint doesn't do anything to your model. You'll get the same answer. But if you had an optimal solution and some of them were further away, by imposing this new constraint that you have a distance or a proximity relationship, it will have to change what the optimal solution is because we have to meet all of the constraints that we put into the model. So this second paper also talks about using optimization in concert with simulation. So what they'll call the network simulation step has, in addition to all of the inputs we already discussed for this optimization study, we need all of those data points as inputs. Often some of the outputs of the optimization model can be used as inputs to the simulation. For example, the modes of transport that I'm going to use, who supplies who, the kind of the network design. These are all inputs to the simulation model. But in addition to those, I have to get to a finer level because the simulation is not as strategic. It's more also at the operational level. I have to actually look at my business rules or policies of how I manage inventory and how I replenish inventory. The optimization model could recommend inventory level settings. It might just say, this is how much you need to keep in order to meet demand. But the actual process of how you keep it and how you replenish it is modeled at a more detailed level within the simulation framework. I could have policies besides just, I'm going to move this much goods by this mode of transport. I could actually have some sourcing or transportation policies that are much more specific, much more detailed in my simulation model, where I could look at things like dwell times, gate appointments at the distribution center, and a variety of other things that come into play at a more operational level for my transportation policies. The big key in a simulation model is that in a strategic study, the optimization side, we might just have gross demand quantities. In a simulation model, we actually are going to have to know how demand arrives over time, how our customers come to our store, how we consume rebar at an EPC or a job site. The idea here being characterizing time-dependent demand is one of the powerful benefits of a simulation study where we can have some uncertainty. We don't have to say it's 3 every day. We can have a probability distribution. It's a beta distribution with this parameter, or it's exponential, or it's triangular. But the fact that we have time-dependent demand data, we need to use it because in the simulation model, it gives us the opportunity to use these stochastic elements, these non-deterministic elements, and these real policies and the dynamics that exist in real life so that simulation model studies things at a much finer level, at a much higher level of fidelity with reality. So let's compare these two. I've reproduced a table that was in that second paper here, but it was just kind of illegible, so I wanted to key it in here. So for network optimization, it's evaluating a large number of alternatives. Right, because an optimization model is going to trade off and prescribe for you of all the different ways you could do it, what's the optimal way to do it. Whereas a simulation model, you might run a specific alternative with a lot of detailed dynamics and probabilistic information and analyze it for how the supply chain is going to function with cycle times and inventories and WIP levels, etc. You might make some changes and run another simulation study. Optimization is going to sort through hundreds, if not thousands, or hundreds of thousands of options, trying to figure out the best way to do it from a strategic standpoint. The structure of the supply chain comes out of an optimization model, but how the model behaves actually is what, and the dynamics of it, I'll call it, is what the simulation model gives you. While the optimization might give you higher level or aggregate network statistics, simulation gives us detailed performance statistics. We'll get estimations for actual product flow times between nodes, both means, standard deviations, because in a simulation model, as you've heard in 855, we're actually generating entities and flowing them through the supply chain and simulating or emulating real practice. So we have all of that rich data. We can get a variety of detailed statistics based on them. The idea that he says network optimization has no complexity or variance, I think the no variance is more important here. There's obviously complexity in optimization models. But the fact that there's no randomness in the data on the optimization side, we can use the optimization to lay out the structure of the supply chain, to prescribe how it should be designed and configured. Then we can use the simulation to kind of see, all right, if we did it that way, what are the real dynamics? How is it going to actually behave in practice given all of our rules and policies? Here again, prescriptive versus descriptive modeling. You know, simulation, if you give it the inputs and say go, it'll describe what happens. It doesn't tell you, you know what, you should really not do this on a truck, you should put this on a train. Optimization prescribes how things should work. Simulation emulates or describes how things should work. While the optimization model determines the structure of the supply chain in terms of relationships and nodes and arcs, the simulation is once I have the network designed, I can use it to kind of fine-tune and tweak how things are actually going to perform in the supply chain. So it's useful for helping me make more final supply chain decisions, if you will. So let's consider an example supply chain here. An example air distribution network. So let's say I have some kind of origin location. Could be a warehouse, could be a distribution center. But I have an origin, and by truck, I'm going to take it to an airport. Now, these numbers on the arcs here, 1 to 2, we'll just say are in days. Do I think it takes 1 to 2 days to drive something between a warehouse and an airport? No. But there's all kinds of time that's usually required to build the load the truck, get the bill of lading generated, get the driver, drive. DOT regulations require only so many hours a day they can actually be working behind the wheel. Then we got to get it to the airport. We have to get it unloaded and staged. So go with me here. We're going to say that 1 to 2 days to get stuff from an origin to the airport. Problem is, it might sit at the airport for up to 7 days. Because just because I get it to the airport, there could be some delay as we get other shipments from other people and have to consolidate them, verify them, potential customs issues, tariffs, duties. But there's some delay typically with sitting at a location prior to actually flying to a second airport. Well, here's where intermodal logistics, right? I've already used a truck to get it to an airport, then I used an airplane to get it between airports. If it's international, what has to happen here? Well, I have to be at least in 2 countries with these 3 nodes. So again, 3 to 4 days from airport to airport. Why? Well, could be the travel time, could be intermediate stops, maybe you have a crummy plane, maybe you have customs issues. From this airport, this may sit another 7 days because that's the reality, right? Things don't just fly right through like we want them to, where in a textbook study that we would teach undergraduates, you know, the supply chain has a very nice structure and all of the times are deterministic and things flow and, you know, nice and happy. But in reality, we know things sit for a variety of reasons. Maybe then we take it by truck to a distribution center from the airport that could take another 1 to 2 days, where we take the goods that came in from a variety of different origins to our airport. Maybe not from airport 1, but maybe another airport shipped into airport 2. We're doing some consolidation here. The idea is at this DC, it could also sit for a couple days, where finally we could, by local delivery trucks, maybe over a period of 5 days, get everything delivered out to our customers by smaller fleet vehicles, local city drivers. We could have a different customer that takes only a single day. We could have a third customer. We could have end customers. But this example network here is a simplistic representation of what? Well, it's multimodal logistics. There's lots of steps and processes embedded in each node. But hopefully you'll believe me that at a high level, at a strategic level, this is the level we're going to be modeling things. I don't right now know the name of the driver who's going to be driving any of these trucks. But it's kind of not relevant to me when I'm looking at a strategic study to figure out, based on my demand, how many flights am I going to have to take? How many trucks do I need? How many trucks do I need for each air flight? What is the delivery schedules we should plan to promise to customers 1, 2, and 3 in order to get them their shipments as quick as possible, potentially, after they arrive at the DC? If I look at all of these durations throughout this graph, you'll see that the minimum transit time is estimated at 22 days, excuse me, from origin 1 to customer 2. The maximum transit time could be up to 29 days from origin 1 to customer 1. Now, often those of us who like things like Amazon Prime and quick shipping, we place an order and we get it in 2 days. If you think about it, when we place that order to get it in 2 days, it's this piece of the puzzle. It's Amazon ships it from a DC directly to me. They've already gone to the trouble of sourcing it from around the world, storing it in their various distribution centers, because they might have 5 to 10 different distribution centers throughout the United States, throughout wherever, that are strategically located and strategically stocked with the right materials, such that we can respond to the customer quicker. Okay? So you might remember a while back, Amazon went to free shipping for the first time, but they told you it'd take 5 to 9 days. You could pay for 1-day shipping. You could pay for 2-day shipping, a little less. But you could take free shipping if you'd wait 5 to 9 days. Now, I know around the holidays it's often free shipping based on some dollar threshold, but hold on with me here for a second. The reason Amazon can go to a 5 to 9 days delivery time, but give you free shipping, is that if it has 10 distribution centers throughout the United States, it's possible that my order of 4 things could be sourced out of 4 different distribution centers, each item in its own location, because that's where they already had it. And they're willing to let me take a little extra time and not charge me, because they can more economically ship it from where it already exists direct to my house. Maybe I'll get 4 separate boxes. If I want to do it quicker, maybe they will do extra handling, ship it from one DC to another DC to bundle it together to me. Maybe I can't pick it from the most advantageous DC that has the most inventory. Maybe I'm going to pick it from the DC that's really close to me, DC here being a distribution center, such that if I'm going to pay for the shipping, I'm going to get it to the customer quicker from the closest distribution center. But if they're willing to wait, maybe there's a distribution center out on the West Coast that has tons of these things. And we're going to source it out of there because the distribution center that's closer to me doesn't have as many items in stock. So there's a variety of incentives or reasons that companies like Amazon and other what I'll call supply chain distribution leaders do to incent or incentivize customers to take longer delivery times for less or no shipping costs. And it's typically looking at their entire supply chain, what's stored where, different modes of transportation, and what's the most effective way to get it to the customer cheaply, minimize their cost, or, oh, by the way, if I'm willing to pay the expedite cost to get it in a day, then they're going to be willing to step up their transportation costs on their side because I'm willing to pay that premium. So this here was our air network. Simplistic to start, multiple modes of transportation, delay times at the nodes, transportation times on the arcs. Okay, so let's look at a maritime network. So I still have my origin, but now I'm going to take my stuff to the port. Why is that? Well, I got to get it to the port to get it on the boats. And depending on where I'm sourcing things from and how many origins I'm driving to the port, let's say it's a 5 to 10 day process to get everything I need picked up, assembled, and get it to the port. It could sit at the port for 2 weeks. Maybe to get containerized, maybe to pass customs, maybe they just are busy with other things. Again, there's delays at each step along the way here, such that finally, maybe I can sail the ship. Maybe that 14 days is because there was no sailing scheduled. It's for 14 more days. But this ocean voyage on a big container ship could take me 30 days, depending on where I'm going around the globe. So if there's a 30-day delay from port to port, guess what happens when I arrive at port 2? You guessed it. I'm going to be sitting again because potentially it doesn't just come right off the boat, get on the truck, and drive out the gate. You know, there are delays in the port. There are many different things at the port that have different priorities. They pay different costs, such that we could have some delay before the port gets it on a truck. Here's an example of a container being loaded onto a flatbed truck and take it to a warehouse, where once it gets to the warehouse or distribution center, it has to get taken out of the container, sorted, broken down. This could take a 5-day process of transporting another 5 days, or a collective 10-day potentially, to get everything at the warehouse in our hands in a usable quantity such that we can then take some of it to a distribution center, and from there, after some amount of delay, get it to the same customers that you saw before. So we had an air network that was intermodal. Here is, I would assume, an international network. That doesn't mean we couldn't take things by boat from LA to the east coast of the United States through the Panama Canal, but typically companies wouldn't do that. When they're looking at maritime, they're going across continents because it's far cheaper to put things on a train across our country than it is to sail, plus it's faster. Maybe it's not cheaper to put it on a train. Let me take that back. It's faster to go on a train across our country by train, by truck, by air compared to the ship. I do not know about shipping costs across the United States because if we're shipping in the United States, we might be looking at inland waterway and barge traffic. But often when we're looking across different continents here, we do have this idea of going from port to port, whether we're shipping things from the U.S. over to Europe or Asia, things from Asia to the U.S. and so forth. So if you put these two networks together, you'll look at, first of all, we have a 77-day time or an 88-day time on the port side, on the maritime side. So the same distribution network with different options to get it to that DC could take much, much longer. Might be necessary depending on what the goods are, might not be necessary. Different transportation options exist at different costs and different time frames. But as I was saying, if I put these two things together, you could have your multimodal or intermodal distribution network where you do have the option to source by the water or by the air, getting things to eventually your DC where you can actually get things to a customer. Now, this example would probably be best explained by we're shipping stuff out of Houston and we want to get it over to the Middle East. So yeah, I could fly things between airports at a very expensive cost, but boy, could I cut a lot of time out of it. Because remember, this upper leg was a 22 to 29 day, the bottom one 77 to 88 day. Well, if that's the case, what else is there? Well, often there's additional realities. Now, this may not be the case here for going from Houston over to the Middle East, because I don't think there's a train that can go from Houston to the Middle East directly, at least I hope not. But depending on the network, depending on your realities, there could be other options besides just one or the other. There could be something where you could go direct to the DC by truck if you didn't wish to fly it. There could be a train that you could take. So there's all different ways and options that these networks can be configured. What we're doing in a supply chain optimization model is we're giving it all of the potential connections, all of the potential nodes, arcs, time delays, costs, the different ways to get stuff from A to B, A to C, A to D, etc. And then telling the model, okay, I want you to tell me what's the best way to route my goods, by which modes of transportation, through which locations, from which suppliers, etc., so that it's the cheapest possible to me. It's cost optimal, if you will. And where I'm going in subsequent lectures here is a case study of some research I did for a large retailer where we actually did this entire type of examination here. And I want to show you how this actually happens in practice, kind of my own case study, if you will. Before that, a couple more slides to kind of get your mind around this idea of nodes and arcs, if you will. If you think about a road and rail network, you would have local distribution facilities, local warehouses. You would have trucks bringing things to the rail terminal. Even each of these triangles might have a little city driver, if you will, that has to go and pick up packages. So maybe this is UPS picking up packages at office buildings, getting them to a UPS hub. They drive a truck to the rail terminal. They gather their own stuff and drive a truck to the rail terminal. Once all of these road haul partners have brought their goods into the rail terminal, we build the train and we do the rail haul from LA to Charleston, for example. At the rail terminal on the other side, We can then send out by road all of the pieces going to their intended destination, such that with this network, with 2 rail terminals, I can connect a variety, a plethora, if you will, of sources and demands by doing pickups, consolidations, getting them to the train, training them across the U.S., and then breaking them back apart, and then getting them distributed by rail out to their intended destinations. So we have this nodes, which are the triangles and the squares. We have the arcs, but each of them in this picture are representing different modes of transportation, different speeds, different capacities, as well as different costs. Consolidation is a big deal. We do this a lot in supply chain optimization and in practice, because if we're going between 2 points, I want to make sure that I take advantage of gathering things together, consolidating things together, such that I can make as fully utilize my transportation resources, my transportation assets, rather than shipping one thing to this triangle, this thing to the next triangle, this thing to this triangle, before you know it, the number of combinations just get explosively big. So point to point, we have line hauls where we have different consolidation along a fixed route, and I might have other facilities get involved. There could be this idea of collection going to another higher level of echelon where I group and aggregate again, another level of consolidation here. Then I make the point-to-point haul and break it down. And finally, a very popular type of road network, or air network, or rail network, or intermodal network is what we'll call it, a hub and spoke. Hub and spoke, think about a bicycle where you have the center of your bicycle wheel, this is the outer edge of your wheel, and we connect things together such that these 6 suppliers or receivers are connected with these 6 suppliers and receivers with a total of, so here's 6 edges or arcs and 3, so that's 9. So there's 9, so there's 18 arcs in this hub and spoke network. Is 18 good? Well, think about it. If you tried to connect all 6 suppliers to all 6 receivers independently, how many arcs is that? Well, that's 36. So rather than having to establish 36 different paths, different transportation relationships, transportation lanes, we often use consolidation to try to bring things down to a manageable level so that we can make our transportation more cost effective, because there may not be a lot of goods going from this one supplier to this one demander. But through the hub, I can bring stuff into the hub, consolidate it into the right size trucks, the right quantities, the right timing, and ship them back out. The last paper I had you look at, which those figures are also from, talks about opportunities for research in intermodal logistics. Finding the optimal number of terminals. This is that site location part of the problem where you give me all my candidates, and the optimization model could tell us where the terminals should be placed. This is a very challenging problem when you think about different modes of transport and the global nature of the problem. Also locating the hub terminals in a hub and spoke network. Figuring out what's the best way to do consolidation. If you figured all these 3 things out, we have to get down to a finer level when we're actually looking at, in a specific terminal, how we allocate our capacities and how we schedule the different jobs and the people and the forklifts and the other equipment to most effectively optimize the facility logistics, if you will, inside the walls of the building. So we could be looking at things from the entire supply chain all the way down to inside one of the, in our global supply chain model, it's a single node. We could be optimizing inside of that node all of the different detailed activities that are going on inside of it. Finally, figuring out, if you had all these things figured out as well, or independently, the size of the truck fleet you need, how your drayage operations are going to function, how many drivers, what kind of trucks, different hours, modes of operation. This is a really interesting, challenging problem that's faced by many different industries, not to mention capital projects industry. And these type of research opportunities, I think, are going to be around for quite a while, because solving the problem generally is typically easier than solving the problem practically with all of the reality constraints of bringing in all of the different things we have to deal with in terms of our own supply chain, But these optimization approaches can be very useful to design and lay out effective networks. And as mentioned, the simulation approaches can also be used to really fine-tune the operational policies and look at the dynamics and how demand evolves over time, how our optimization designed network is going to perform for us. With that, I'll bid you good day, and I look forward to the next lecture.